Hello and welcome. Today's presentation is brought to you by Science Visualized. Today we're looking at covalent bonds. Anytime you see that word covalent bonds, it means they are bonds formed by electron sharing. So electrons are shared. And there are two types of covalent bonds. The first one is symmetrical covalent bond, and the second one is polar covalent bond. In symmetrical covalent bond, the electrons are equally or uniformly shared, and this is formed when you have two elements or atoms with equal or very close electronegativity. So for example, hydrogen and hydrogen, if you write a Lewis structure for that, you'll see that the electrons are equally shared. They're exactly in between the two hydrogens. But when you look at polar covalent bonds, the electrons are not equally shared. And that's because the two atoms involved have different values of electronegativity. So elements with higher electronegativity will pull the shared electrons strongly towards themselves, say X and Y. And if Y is higher in electronegativity value, then the shared electrons are going to be closer to Y than X. So we will write the shared electrons being closer to Y than to X. And because of that, you end up with a higher electron density closer to Y, so we put a partial minus, delta minus on Y. It's not a full negative charge, it's just a partial negative charge. And then because X has a lower electron density, we put a partial plus on that. So it's almost like a positive charge, but it's not fully positively charged. So we can use delta minus and delta plus to indicate a polar covalent bond. The bond between X and Y is polarized. The other way to indicate a polarity is to draw what we call a dipole, where the head of this dipole arrow faces the partial negative, that's a higher electronegative element, and then the tail, you cross it to look like a plus. The tail is on the side of the partial plus. Now the electronegativity value increases from left to right on the periodic table. So from left to right, that means fluorine will have higher electronegativity value than lithium. So fluorine is higher than lithium. And also it increases up the group. So that means fluorine will be higher than chlorine. Same thing here, sodium, Na, is higher than potassium. Now let's apply this. When you look at carbon-nitrogen bond, so carbon is in group 4A here, nitrogen is in group 5A, we see that nitrogen is further to the right of carbon, and therefore nitrogen will be higher in electronegativity value, and therefore nitrogen will have a partial minus, while carbon will have a partial plus. Or you can use the dipole arrow, where the head faces the partial minus nitrogen and the tail faces carbon. We can do the same thing with carbon-oxygen bond. Looking at carbon, that's group 4 again, that we just saw, but oxygen now is group 6, so oxygen is to the right of carbon, and therefore oxygen is going to be partial minus, and carbon will be partial plus. Or you can use a dipole arrow, with the arrow facing oxygen, which is high in electronegativity, and then the tail facing carbon. For HF, we see that hydrogen is in group 1A, while fluorine is in group 7. So that's fluorine there. So fluorine is further to the right, and therefore it's going to be higher in electronegativity value, and we can use either the delta or the dipole arrow. So in this case, we're just using the dipole arrow. Now, if you only have one dipole in the molecule, like this HF has only one bond that's polarized, that means mu, that's called the dipole moment, does not cancel out. So you have a net dipole moment. So you say the dipole moment is not zero, and therefore that molecule will be polar. If you have more than one dipole arrows or more than one bond, then you have to resolve. You have to add all the dipoles to see if the result is 0 or not. So if you have water, for example, H2O, we know that the central atom is oxygen, so you write oxygen there. And that oxygen we know is bonded to 2 electron pairs and also bonded to hydrogen. And because that oxygen is bonded to 4 things and all of them are single bonds, there's no double or triple bond, then we say that that oxygen is sp3 hybridized, meaning that its structure, its geometry is going to be tetrahedral. And you know that tetrahedral geometry means that you have 2 elements, 2 atoms, like in this case the 2 hydrogens plus the oxygen on the same plane, and then you have the other 2, one going in and the other going out. So we're going to put one of the electron pairs going in and the other electron pair coming out. So that's a tetrahedral geometry. Next, we show the dipoles. We know that oxygen is further to the right of hydrogen, and therefore it's going to be high in electronegativity. So the dipole arrow faces oxygen like that. But the electron pairs are even stronger in electronegativity, and therefore you have a much larger dipole arrows like that. And when you add all these forces, you'll see that these 2 hydrogen dipoles, the resultant is going to be something like that. And then the electron pair, the resultant for that, will be something like that. So when you add them together, it becomes mu, which is not equals to 0, which is actually something going up like that. And because of that, you have a very large mu or dipole moment, and therefore you say that water is polar because all the dipoles do not cancel out. Or you can say because it has a net dipole moment. Thank you very much for your time. Please consider supporting the channel by subscribing and also liking the video.